2. Come on, baby. Okay, we are going to talk about nuclear energy today, which makes it extra special that we have a Nihonjin here today because we're going to talk about the bombing of Hiroshima and Nagasaki, which probably means more to her than it does to most of you. But we're going to talk about nuclear energy. Oh, by the way, it turns out that our homework site doesn't have any homework questions for me to assign, so we're done with homework. But you do need to do all of chapter 33 for Concept Coach for class on Wednesday. Yeah, it's not my fault that we don't have homework, but like I told them, I don't think my students are going to complain. There is a homework assignment due tonight. Yeah. Yes, the cheers all around. Okay, so we're going to talk about nuclear energy. Nuclear energy is vital for life, right? We have the sun provides over 99% of our energy budget on Earth, and that is not the energy that we're specifically using per se, although in the end it comes from that. But the energy that the Earth receives, about 99%, comes from the sun, and that's from nuclear fusion, from fusion of hydrogen to helium. The small remnant is primarily nuclear fission of things in the Earth's core producing energy. So we're highly dependent on nuclear energy even if it's not coming from nuclear power plants. Nuclear energy, I talked about this before. We talked about the binding energy per nucleon. We did that calculation. And anything that moves toward a higher binding energy per nucleon as a result of a nuclear reaction is going to release energy. And so that means I could start down here and move that way and release a lot of energy per mass. I could start on the other side and move this way, release energy per mass, but it's going to be a smaller amount of energy that's released. So fusion is a much better source of energy because you can release a lot more energy per mass of the fuel. Fission, less. Fusion is merging two nuclei together. Fission is breaking a nucleus into smaller parts. So we're going to look at those two things today. And we'll start with a preconceived notion question. Actually, you should know the answer based on what we've talked about. Which process has the potential for more energy per mass of fuel? Yeah, I just answered it, actually. What was the question? Okay. Okay, 7 people said fission has more, 7 said fusion has more, and 1 said that fission and fusion are the same. Look at the graph. Talk to your friends. Go ahead, help her.
She's not my friend right now.
What is your name?
I'm Juna.
Juna. And I'm really rusty. Nihon de... Doku ni sundemasu ka? In Osaka? I did not go there. I spent 2 months in Japan doing research. Yeah. As I'll say later, I was in Hiroshima on the anniversary of the Nagasaki bombing. So it wasn't on the anniversary of the Hiroshima bombing, but I still had some drunk old man in my face. Okay. Assuming that you all had a good discussion, let's repoll this and see how things came out. Okay, on Repole, we had more people went with nuclear fusion. I know I heard Reagan explain it, so I'm going to ask Reagan to explain to everyone, why did you come up with fusion?
I was just looking at the graph.
Just look at the graph, and what aspect of the graph?
It's real steep, so that's going to be more going on there. If you were to go, what I'm trying to say, if you go from hydrogen to helium, it's a bigger jump than you would go from uranium to radium, and so that's just there. If you went from helium to the next one, it's going to be a bigger jump from whatever to whatever. Fusion's going to be bigger than fission.
Okay.
Very elementary.
The difference in the height, going from hydrogen to helium, he pointed out. You have a difference going from hydrogen 2, right? If you went from hydrogen 1, you'd start at 0. You have a difference of about 6 mega electron volts per nucleon. Whereas if you were going from uranium to, let's say it was possible to go to iron from uranium, you'd only have about 1 mega electron volt per nucleon. So you would have 6 times more energy per mass available from fusion than you'd have from fission. Thank you, Ray. Okay, so looking at the fusion process. The fusion process is 2 nuclei merging into 1. Now, tell me about the charged state of a nucleus. It's positive. So we're going to have here something that's positive, and here's something that's positive. What kind of a force do I have between 2 positive things? Repulsive. They're pushing each other away. So what happens to the strength of that force when they get closer? It increases. So that means the closer I get them, the more they're pushing apart, the more energy I'm going to have to make them keep coming closer. How in the world can I make them merge if they get more and more repulsive if I try to bring them closer and closer together? And that force does approach infinity as you get them to 0 separation. So how can I actually make them fuse? Well, that was about stability in the nucleus. It's related to that, but that's not the reason. How can I actually make them fuse if they're repulsive because of electrostatic forces? Big clue. Electrostatic is not the only force in the universe. What are the 4 fundamental forces? Gravity, electrostatic. The strong and weak nuclear forces. Are the strong and weak nuclear forces attractive or repulsive? Let's just talk as the nuclear force. It's attractive. So why didn't I talk about the strong nuclear force when I was talking about my first picture? The nuclear forces are extremely short range. They're just nucleon to nucleon. If I have something in between, it won't affect. They have to be right next to each other. And so that's where Jaron's answer came in. To make a stable nucleus, you put in neutrons to space out the positive charge of the protons. Well, if we can get the 2 nuclei so close that the attractive nuclear forces start weighing in, then I can cause fusion. But in order to get them so close, I have to have them really pound into each other hard. If we're talking about a gas, what measurement is going to tell us how fast they're moving, how much kinetic energy they have? Temperature. So in order to make this occur, I'm going to have a high temperature. At a low temperature, the repulsive forces is going to be enough to keep them from coming together. At high temperature, you can force the 2 nuclei close enough together for them to have fusion. So that's one thing you need for fusion. You need high temperature. Here they fused. Success. Here they did not. Now, of course, high temperature then is necessary. It's absolutely required to have fusion. I say absolutely required, as far as we know. If you heard the term cold fusion, the term cold fusion is the goal of trying to find a way to energetically be able to bring these two nuclei close enough together for fusion without having to have them smash into each other really hard. The ideas people have are you have crystals, and crystals you have lattice positions, and they think maybe you could have interstitials where you get energetically, I put one hydrogen here in the interstitial, and then I have another hydrogen that also comes and shares that interstitial position. Interstitial means a place between the lattice spots. And if it's energetically favorable to have the two sharing in there, we might be able to get them really close without having high temperatures. That's the kind of thing that people are studying when they're trying to study cold fusion. How to make fusion happen without super high temperatures. There's a second thing we need for fusion besides high temperature. What do you suppose the second thing we need is? What do you suppose? What do you think? You could be wrong. A what? Okay, some way to contain it. Now, to make fusion, you don't have to contain it. If we're going to make a fusion reactor for power purposes, you have to contain it. We need high pressure. We need high pressure because high pressure means that I have molecules hitting a lot. Right? If I have high temperature, but there's only two molecules in this big container, the chances of those two molecules hitting each other is small. But if I have high pressure, the chances of molecules hitting each other becomes much higher, and that then increases the probability that I will have fusion events. So I need high temperature to be able to have fusion. I need high pressure to make it likely to occur. Right? High temperature, low pressure, it's possible but unlikely. High temperature, low temperature, high pressure, it's impossible, but it's likely to come together. They just won't stick. High temperature, high pressure is what you need for fusion to occur. So I have another clicker question. Why must high temperature be achieved for nuclear fusion to occur? We had two requirements. This one is asking about the requirement of high temperature. Okay, the late changes brought us to essentially a balance here. Once again, this is a good one to discuss with the person near you who was paying attention.
It does increase the energy though, right? But that's not the main thing.
Something about
Because it's not going to get any closer. Yeah.
All right, let's see if your friends helped or hindered you. So answer again for those who didn't. Okay, 2 people got help. A few others got misled. We needed high temperature to give them enough energy to get close enough for the nuclear forces they're attracted to take over. Without high temperature, they can't get close enough. They don't have a high enough kinetic energy to get them close together. What was that? Sorry. D, yes. Wait. No, it was. Whoa. I should read more carefully. To allow the nuclei to get close enough. Yeah, I said B. You're right. So I actually went the wrong way. I wasn't reading carefully. That's a bad thing for a teacher. Yes. Thank you for correcting me. At least I said the right words. I just circled the wrong one because I didn't read. So the sun. The sun is our only controlled nuclear reactor that's a fusion reactor. It's controlled. What controls the sun's reaction? Gravity. Gravity is compressing the sun, get high enough temperature and pressure in the core for fusion to occur in the core, pushes back out, and then you have what we call a hydrostatic balance throughout the sun of the pressure caused by the explosion inside and gravity pulling in. The sun is then releasing energy, primarily in the form of photons. And those photons go a very short distance, and then they get absorbed by something. And then it re-emits the energy in another photon, maybe a little bit lower energy photon. And the direction could be any old direction. So calculations suggest it takes about 1 million years for energy from the fusion in the core of the sun to make it out to the region that we call the convection zone. Inside here is the radiation zone. Outside is convection. Remember, we talked about radiation, electromagnetic waves. Convection, hot material floats up, cold material floats down. The intersection doesn't have mixing, and so it's only radiation. It takes about 1 million years to get there. Then it takes a fairly short time in the convection zone because it's hot, it floats up. So roughly 1 million years ago, a fusion reaction in the sun produced energy that we're now receiving as sunlight. Question?
So if the sun was to die, 1 million years would pass before we realize it?
When the sun dies, so to speak, it's actually a process that takes time. What happens is you have, like a car, you have gas in the engine. When you run out of gas, it doesn't actually stop instantly. It starts sputtering. Right? You get a little bit of gas, fires, then nothing. And there was a little another. The sun's going to do like that too. Its reaction rate's going to slow down. And as the reaction rate slows down, the pressure outward is going to drop quickly. And as the pressure outward drops, it's going to be crushed by gravity and shrink. But as it shrinks on the inside, it's going to actually have as a side effect releasing energy into the outer portion to make it expand. So the sun will actually expand when it's dying. But as it expands, it cools, so it will be giant and cooler. What color is cooler than white? Red. So the sun will become a red giant while it's dying, while it's running out of fuel. And it takes a long time for the process to taper. And then eventually it will actually get high enough temperatures and pressures to fuse helium into carbon in what we call the triple alpha process. And once that happens, it'll reach a stability. It'll have a second main sequence life, if you will, that will last for, instead of 10 billion years, it'll last something like 1 billion years. And then after that, it'll be done. It'll shrink down, give off a big shock wave. We will be incinerated. When it's a red giant, we'll probably be inside the sun, so we won't be living here. The earth will be inside the sun. You and I will probably be in heaven, right? That's my belief. Okay, moving on from the sun, how do we know that the sun has fusion going on?
Energy.
Okay, let's think about the scientific process. We had, I think it was Hans Bethe and George Gamow and I can't remember the three guys wrote the famous paper, the Alpha. Guy's last Ralph Alpher, so they put their names in order of Alpher, Beta, and Gamow. So it was the Alpha Beta Gamma paper. Anyway, they came up with a theory. They got a Nobel Prize for saying that the only way that the sun could produce energy in the copious quantities it is if it was fusing hydrogen to helium. And of course, you don't get your Nobel Prize instantly for coming up with this theory or hypothesis at this point. What has to happen next in the scientific process? You got to do experiments to test it. So, well, we can do some experiments on Earth to test what happens with fusion, but how do we know that that's what's going on with the sun? Our hypothesis has to make some predictions that are testable. And one of the testable predictions was that during the production, actually it's the production, I think, of deuterium in the proton-proton sequence of fusion that we believe is occurring in the sun, it kicks off neutrinos. And neutrinos, I've already told you, they're little tiny things that have no charge and very low mass that are passing through us constantly. And they just don't interact with us because they're so low mass and no charge. So we don't worry about neutrino radiation because it doesn't affect us. But they said there should be neutrinos coming from the sun. Using the amount of energy that's being released from the sun, they can calculate how many neutrinos per second should be coming from the sun. Using geometry, they can calculate how many neutrinos per second should be going through a square meter on Earth. And so then they have come up with ways of measuring neutrinos. So here's an example of how they measure neutrinos. You have a bunch of deuterated water. That is water that has, instead of hydrogen, deuterium for one of its hydrogen atoms. Why deuterium? Because there's a really low probability that the deuterium will absorb an electron neutrino and give off a flash of light. And so this tank, it's a huge tank. They usually take like old mines and they put photodiodes, things that will detect, not photodiodes, photomultiplier tubes that will detect light in the tank, all around the tank, fill it up with the deuterated water, and then they look for these flashes of light. And that's how they measure neutrinos. Now, it's a very unlikely event to even be measured. Even if a bunch of neutrinos come through, it's like 1 in 10 to the 20th probability that you'll detect it. But as long as you know your detection or efficiency, you can calculate how many really came through just based on what you got. So they set these things up, takes a lot of money, and they measure the electron neutrino flux coming from the sun. And they found only 1/3 of what the theory had predicted. What does that tell you? You had a prediction from your hypothesis. You test the prediction, and it comes out wrong. What do you do next? Revise the theory, probably. Now, I said this is what's going on. Somehow it worked out. It wasn't until the late 1990s when the Supernovae, I think that's how you pronounce it, reactor in Japan actually measured a mass for neutrinos. And if neutrinos have an actual mass, before that they weren't sure if they had mass at all. If they have a mass, then the particle theory says that the neutrinos can actually change between 3 different forms: electron neutrinos, mu neutrinos, and tau neutrinos. But they were only detecting electron neutrinos. And in the time it takes for the neutrinos to go from the sun to here, they should have completely randomized, so only 1/3 of the original electron neutrinos would be electron neutrinos when you get to the Earth. And then so suddenly here in the 1990s, all of a sudden, boom, we have experimental evidence that their prediction was right, that it really is the right number of neutrinos. And so now they got their, it was before the contradiction had been determined that they got their Nobels. But now we're really quite confident because we have some experimental results confirming predictions. And it even makes you feel better that initially they thought that their experimental result was incorrect. So it's not like they were, you can't say, they fudged the data to try to make it work. They found new information and then revised their understanding of the particle physics. But that revised understanding of particle physics suddenly made their experimental results actually what was predicted if they had known well enough what was going on with particle physics. So the neutrinos is an important part of our understanding of why the sun is fusing hydrogen to helium. Supernovae are things that produce copious amounts of neutrinos in one fell swoop. A supernova occurs when you have the core of a star collapse completely. No force known to man can stop the pressure of gravity at that point. And it forces electrons to merge with protons, and particle reaction occurs that makes neutrons and neutrinos, and so you get huge amounts of neutrinos from supernovae. And what we do now, we not being me, but scientists, they use these detectors, and every now and then they'll see a spike in neutrinos. And when they see that spike, they use different detectors on Earth to try to triangulate where it came from, and they say that spike must be the result of a star that's just collapsed, it's just undergone supernova. Now, just like that question that Toussaint asked, when you have a supernova, it takes about 3 days before any sign of the explosion in the core reaches the surface. And so you get this splash of neutrinos, and then they start looking out there and hoping that somewhere around 3 days later, they'll actually see the supernova occur. Because the neutrinos just go right through, it doesn't slow them down at all, because they don't interact. Cool stuff, I think. So now, how could we use this? There are big goals to try to make fusion reactors for power. Why fusion reactors? Well, we've already studied one, much more energy available per unit mass. Another one, we have fuel for fusion reactors readily available. If you just took, the top inch of ocean water around the Earth, and you took out the deuterium that's naturally occurring in that top inch of ocean water, that would be enough fuel to power the Earth for something like 100 years for all of our uses. Right? We have lots of fuel available. Another really beautiful outcome of the fusion reaction is you don't have a radioactive byproduct. After the fusion reaction occurs, you have stable helium. Nobody's scared of stable helium. We breathe it in and make our voices funny. So there's some real big advantages for fusion reactors. The problem is controlling it. So this is a diagram of the ITER. It's a tokamak, a Russian design, probably that's a Russian word, the tokamak, that uses a torus. I think of a torus as a donut, right? It's a donut-shaped reacting vessel. It uses magnetic fields to contain the particles in there and allows you to get the high temperatures and pressures necessary for fusion. And once you get fusion inside, of course, what's going to happen to the temperature inside when fusion occurs? It gets really hot because you released a lot of energy. And then you use that to heat water and run a steam generation plant. That's one approach to trying to make a fusion reactor. It's not there yet. We also have inertial confinement. I've been lucky enough to visit 3 separate inertial confinement laboratories, 2 at Lawrence Livermore National Laboratory, their earlier NOVA, and then the later National Ignition Facility, NIF, that's shown here. And also when I was in Japan, when I was down in Hiroshima, I visited a similar one they have there going. What they're trying to do here, you can't tell what's going on in these pictures, but you see all those pipes? All those pipes are for isolating laser beams. And they start with a single laser pulse, and then they amplify it and split it and amplify it and split it until they have a really strong laser pulse that's all sequenced so it's the same path length, all going to come to the same time. And they have all of these laser beams come and hit one point at the same moment. So you have a huge amount of energy. The amount of energy that's in one laser pulse is, I think they said, enough to power a city for... the power is equal to the power used by an entire city. But it's only for a brief time, for like a millionth of a second. But they use an incredible amount of energy to make this laser beam. You make that laser beam focus on this little pellet that has a little brew of hydrogen and deuterium in it. And the high temperatures and pressures created by absorbing that laser beam causes fusion to occur. Well, you have fusion occurring, and it only occurs every time you pulse the laser beam, so you have some more control. But the problem is you have to replace those pellets. And so an idea that was proposed last time I was at National Ignition Facility, I used to take my students on field trips there because that was close to PUC, was that you essentially have a little spigot that drops a droplet, laser beam hits it, drop another droplet, and that would be how they would make it continue going. They have reached break even, that is, they've reached the point where the energy produced in the fusion was equal to the energy that they consumed with their laser beam to make the fusion. Which means they're getting to the point where you have enough energy coming out, but you still have to be able to make it practical in terms of we can keep it running for a year continuously to produce energy. So it's not done yet. So all of our actual power plants are using nuclear fission. If we have a nuclear power plant, it's a nuclear fission power plant. And nuclear fission power plants, well, we have them here in the United States. You're probably well aware of the Fukuoka, I think it is, power plant that when they had the tsunami, it was damaged and there was radiation concerns there. There was the Chernobyl one you might have heard about where they had the meltdown when I was in college. Or actually, I think it was my senior year in high school. So we have nuclear power plants across the world, and one of the concerns people have is safety. So we're going to look at how these things work and a little bit about the safety. So for fission to occur, we have to have a big nucleus, something that's like uranium-235, and then we have a neutron that hits it. And that neutron has to be going slow enough to have a significant chance of interaction. If I have a fast neutron, it will just go through and not interact. So we have to have a slow neutron. In terms of temperature, what would you use to describe a slow neutron? A low temperature. And so we use the term thermal to say that it's going slow enough that we could treat it as a reasonable temperature neutron, something that's in equilibrium with its surroundings. So we have this thermal neutron. What do the 0 and 1 mean that I just wrote? Mass of 1 and 0 protons. And then we have the uranium-235. Whoops. I can't see what I have there. Okay. Those merge and it gives me uranium-236. Forgot the 2. I put a little star here. Anybody know what that star represents in chemistry? Because it represents the same thing in nuclear physics. It's an excited state. It's an unstable state. So it creates an unstable uranium-236. That thing will immediately break apart. So it's not like, a second later I'm all, yep, there's my uranium-236. It's gone. It's just an intermediate that immediately breaks into 2 smaller things.
So it's just the transition.
So it's a transitory state, right? It has to go to the rest. And I put A plus B. A plus B because we can only calculate probabilities of what it's going to break up into. I can't say it's going to break into this nucleus and that nucleus. I can only say it's likely to break into this and this. They actually have graphs you can find that are something like this for what it breaks into. It's breaking into 2 things. This is the most common for the lower mass, and this is the most common for the higher mass. But it could be this one and this one, as long as they add up to the right number of protons and neutrons. So here we have the fission starting to occur. It's breaking into 2 pieces, and here is my product A and my product B. And those products are going to be generally highly radioactive. They usually have way more neutrons than they would because the number of neutrons per proton is much bigger in large nuclei than smaller ones. So those things break apart, and you have radioactive byproducts. Well, there's a downside right away to nuclear fission. Radioactive byproducts. So you can't just take the output of your nuclear fission reactor and say, okay, let's just go throw this in the ocean or something. We have to be very careful with it because it's going to be radioactive, and if people are around it, it's going to endanger them. A key to fission is chain reactions. What was required to start a fission reaction? I had to have that thermal neutron. And I have to have my reaction produce more neutrons. So this one produces 3 neutrons that can go on to cause other reactions. Now, if I have one reaction produces 3 neutrons that can go on to cause 3 reactions, then that means my reaction rate goes 1 to 3 to what would the next step be? 9 to 27, right? It's going to grow very quickly. And so we actually talk about this thing called the multiplication factor. Reaction. If I was a chemist, I'd write that like, what, RxN? The number of neutrons from a fission reaction that cause another fission. So in this picture here, what would F be for this picture? Okay? I heard a 2. If you look at the picture, you see that for this one it was 3, but for this one it was only 2, for this one it was only 2, for this one it was only 2, for this one it was 3, for this one 2, for this one 2. Right? It's going to have different numbers of neutrons. And in this picture, it would be somewhere around, I'm just going to say 2.5, somewhere between 2 and 3. If that F is bigger than 1, the reaction is going to be faster and faster and faster. We say it's heating up. And if F is bigger than 1 and it's heating up, we call that a bomb. So if F is bigger than 1, you have a bomb. What if F is less than 1? Then it's going to slow down and you have nothing. So for a nuclear reactor, for something that's continuing to go at a constant rate, what does F have to be? 1. So we must have, and it's got to be exactly equal to 1, not 1.001. That's not good enough. It has to be 1 for stable reactor. So we have to find some way to control the reaction rate if we're going to have a stable reactor. We can't just trust nature, it'll keep it constant. We have to be able to control it. We call this critical. If F is 1, then it's critical. So a nuclear reactor should be running at its critical point. If F gets bigger than 1, we call it supercritical. And what does supercritical mean to you? Yeah, bomb, run and hide. Well, it's too late to run and hide. If F is less than 1, we call that subcritical. It's just going to die away. So here's a nuclear reactor design. A nuclear reactor design starts with fuel rods. So you see, let me zoom in a little bit. You see the fuel rods. That's not zoomed in. What in the world did I do? The fuel rods are these blue things. So those are fixed in place. So that's the first thing, the fuel rods. What do we use for fuel rods? There are only certain elements that are really amenable to being used for a fission reactor. Among those are uranium-235. Can't read that. I'll write it separately. Or I believe it's plutonium-239. So those are things that we can use as fuel for the reactor. Now there are reactors they call breeder reactors. Breeder reactors have uranium-235. You have to enrich it. Uranium-235 is a very minor component of naturally occurring uranium because it has a shorter half-life than uranium-238. So uranium-238 is the predominant 99.73%, I think, of naturally occurring uranium. So they have to enrich it. That's where Richmond, Washington comes into play. I worked there for 9 months, working at the lab, well, not at the physical lab, but at the facility that did the uranium enrichment. They took uranium and they made uranium hexafluoride slurry. It's kind of a liquidish state. And then they centrifuged it. Uranium-238 has a higher atomic mass, hence when you centrifuge it, it's going to be on the outside. Uranium-235 has a lower atomic mass, it'll be on the inside, so they separated the uranium through the centrifuge, take the inner part, that is enriched uranium, and that enriched uranium can be used in a power plant or in a bomb. There are lots of different classifications for uranium, and I'm not going into that. Do you have a question, Cassie?
Yeah, was that at Hanford?
Yes, the Hanford site.
Okay, yeah. Cool.
Yes. One Sabbath afternoon, because I had my badge, I went out to the Hanford Reserve, where all of the buried stuff is.
Yeah.
Just so I could say I'd been there. They have things like the trains they used to transport, they just put them in tunnels and buried them because they're radioactive.
Yeah.
And my research was partially funded by trying to do research to determine what's in those waste tanks. Okay, so you have to have the fuel rods. Without those, you have nothing. Then you have something that we call a moderator. And I don't, oh yeah, here. We see the word moderator there. The moderator slows down neutrons. It moderates their speed. What do you use to slow down the neutrons? Well, something that works actually really well is hydrogen because it has roughly the same mass as a neutron. So they use deuterated heavy water. Why deuterated? It's twice the mass. It's not as effective, but it's less likely to absorb neutrons. They use deuterated water as a moderator to slow down the neutrons. Because if those neutrons come out too fast from a reaction, they do come out too fast to cause another reaction, then you're going to have a subcritical situation. But you put in the moderator, it slows them down, and the number of neutrons that can go on to cause a reaction goes up. But of course, if that number goes above 1, you're in trouble. So you have the moderator. If you just had the fuel rods and the moderator, it'd be a bomb. So then you have what they call control rods. You see the control rods here. The control rods absorb neutrons. And those control rods are made so you can raise and lower them. You raise them up, you don't absorb neutrons. What's that going to make your multiplication factor? It's going to increase it. So like when you first bring it online, you're going to have those things raised up some so that initially it heats up. But then you quickly drop them in to a level so you keep that multiplication factor at 1. And so computers are used to control and raise and lower those control rods to keep the multiplication factor at 1 and keep it running critically. The last part of this is simple. You have a heat exchanger that takes the water and uses it to heat up other water, not the same water. Use it to heat up other water, and that runs a steam power generation plant. So a fission reactor is just a steam generator, but it's boiling the water by using nuclear fission. And the reason the water is kept separate is because this water here is the water inside the reactor is going to be radioactive, right?
And also probably more expensive if it's deuterated,
Well, you could start by putting regular water in there. It'll quickly become heavy water. But you don't want that heavy water being released into the atmosphere because that steam plant is going to release steam. Goes up your columns, and it's released to the environment. And you don't want to release the deuterated or tritiated water into the atmosphere or into the groundwater, so you have it locked in. Now let's talk Chernobyl. Chernobyl was highly relevant to me because that occurred, end of high school, beginning of college. And they had a big kablooey event. It wasn't just a meltdown, it was a boom. So when you hear people talk about a reactor core meltdown, what that means is the reactor core got too hot. It got so hot that it melted the concrete, and all of a sudden you're going to have water seep into the ground, and that's bad. But things could be much worse than they were with Chernobyl. With Chernobyl, it got hot and it blew the roof off and just released all kinds of radioactive materials into the atmosphere. Why did it occur? I've heard different talks with slightly different reasons, but what I have been led to believe is the guys that were working there at the radiation plant were actually doing some experiments to see if they overheated the reactor, how quickly they could cool it back down. So they took off the computer controls, overrode it so that they could overheat it. Okay, cool it down. Too late. And human error is what led to that. Generally speaking, nuclear power is very safe. There's a lot less radioactive release into the environment from a nuclear power plant than from a coal-burning power plant. But when things go wrong, they can be drastic. Yeah.
How come people can't live with the radioactive conditions, but like a lot of the wildlife there is radioactive, but they're fine?
The radiation, I don't think I got to this in my lecture. I had all of this actually in the previous lecture, and I don't think I got to it. But we have what we call the RBE, the radiation biological efficiency. And depending on the tissues, things are more or less damaging. And so bone, for instance, is much more susceptible to damage, or bone marrow specifically, than things that have cartilage. So sharks with a large amount of cartilage are, instead of bone, are going to be much more resilient for radiation.
Because I mean, like, there's a documentary about like wolves that live there and they're radioactive, and they'll have the thing going like beep 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 all over them.
Yeah.
And especially the bones, but like they're fine.
Yeah, and we could live there too, some of us. If you look at, for that lecture, I was looking at the effects of the lifetime radiation effects, and for people who were in Hiroshima at the time the bomb was dropped, if they weren't killed by the bomb blast, their chances of cancer through their lifetime increased by about 3%. Now, an increase of 3% seems small. The average person's chance of getting cancer is about 20%. But 3% compared to 20%, it is measurable. And so what you're looking at is long-term effects, more likely to die by a small amount, but we don't want to put ourselves in that situation. And also you have more likely for mutations, your kid could have the extra set of arms. Okay, question about nuclear power plants, and you can answer now. Why do all nuclear power plants produce energy through fission? Better. Come on, Toussaint. There we go. Okay. That is correct. Fission, we can control. We have the control rods that specifically allow us to absorb neutrons and slow down the rate. We have the moderator that allows us to increase the rate. We can control it. Now, shift to bombs. Nuclear bombs. Nuclear bombs rely on making something that wasn't a multiplication factor greater than 1, something that was subcritical, multiplication factor less, become greater. There are a couple methods. Here's one. You take two pieces of mass that are subcritical. What makes a mass subcritical? If I have a chunk of uranium, the neutrons produced from just natural decays and whatnot will go through, and if it's small, they'll largely just leave and won't cause a secondary reaction. But if it's large, they'll be slowed down enough that they'll cause another reaction. And so if you get a large enough mass, then just geometrically it turns out that you're going to have a multiplication factor that exceeds 1 and it blows up. And so the idea is you take two pieces of mass that each one is subcritical. The neutrons are largely just going to get out of it. You smash them together, and combined, they're critical. The neutrons can't escape, and they cause it to go boom. So This gun barrel approach is real simple. You simply put some kind of propellant here, traditional bomb, that pushes one piece into the second piece, making a supercritical mass that blows up. So that's one type of bomb. Another type, the implosion type, where you have a whole bunch of tiny subcritical pieces that you then bring together to form a critical mass. Not very complicated, this whole design, is it? You wonder why they had to spend so much time and effort to make a bomb. Well, it wasn't just to make a bomb, it was to make a bomb that made the biggest boom possible. Right? They were trying to optimize. And here's a picture of the Trinity test, their first nuclear bomb explosion. They made big bombs. Now remember, the bombs were made in a wartime. The Americans saw that the Germans were putting an embargo on communication about nuclear physics and on the materials that specifically could be used to make bombs. And they interpreted that to say the Germans were making bombs. And they were right. The Germans did start it. And so the Americans said, we have to do that too. And so they started making bombs. And the Americans didn't stop. The Germans stopped, largely because Hitler didn't like Jewish people. And they were some of his leading scientists. At least that's what I've been led to believe. We continued on and we made these bombs. And then we did what none of the people really thought about when they were working on this. Drop the bombs. Dropped one in Hiroshima. 3 days later, I think it was. Dropped one on Nagasaki. And the devastation was incredible. One of my high school or grade school classmates, her father, lived in Hiroshima at the time that it was bombed. He happened to have been outside of the city visiting relatives and was walking back to the city on the day the bomb was dropped. And so he's done a lot of, like going to Congress and testifying. But it caused major damage. If you've ever been to Hiroshima, you'll see that you have just a few things, and then they have a museum with really incredible stuff. Things like the wall of a bank. And on the wall of the bank, you see the shadow of a man. Because there was a man waiting for the bank to open. And they dropped the bomb early in the morning just before the bank opened. And when that bomb exploded, you have two things that occur. Number one is that the bomb had a big blast wave. But number two is it emitted a lot of neutrons. One of the things they did was they tuned their bombs to produce lots of neutrons. Why lots of neutrons? Because those neutrons, when they hit people, will damage them. And so the neutrons would kill people. And so this man was here and got hit with a whole bunch of neutrons. Now, you don't feel the impact of the neutrons, but they were absorbed by him instead of the wall. So the wall was discolored where the neutrons hit it, but it was dark. You saw his shadow for where he blocked the neutrons. Now, you can be pretty sure that guy didn't survive. And so there was something like, 100,000 people who died on the day of the bomb blast or within a week. About another 100,000 who survived but had medical problems as a result of the bomb. And so the scientists who had worked to make these bombs, they worked on making the bombs because they thought it was necessary to preserve the American way, that we would all be speaking German and whatnot. I know you're trying to speak German now, but we wouldn't have a choice. And so they did this thinking it was the only way to survive. After it was dropped, they saw just all the devastation, how bad it was. And many of them were like, I will never do something like this again. I thought my science was doing good. Clearly, I was doing evil. And so a lot of those scientists, felt great remorse, tried to do things in their lives to show that science is not inherently bad. It's not inherently evil, but it can be used for evil things. And that we need to be responsible and think about how what we're doing in science can be used. I know I've gone way over, but I want to end with just a question for exploring your own feeling. Okay, the results that you guys said were 9 said yes, and 7 said no. Now, I myself would have answered yes if I'd known only what they knew. But in hindsight, knowing what we know now, would I have? No. Okay. Have a good day. I'll see you guys for lab tomorrow. Some people have asked, you're going to be giving like a 20 to 30 minute presentation. You can use video, PowerPoint, whatever is going to work for your presentation. I'll have the posters. I have them in my office right now. I'll have the posters here for you to point to as well. They're graded. They'll be tabulated this afternoon.
Do you have cordboard or something for mounting the posters?
I actually already have them mounted.
Is there a curve?
No, they're good scores.